Welcome everyone to this JMP academic webinar, all about handling non-independence in your data using mixed models. I'm Ross Matusalem, JMP academic ambassador, and I'm going to be presenting the webinar today. And in talking about mixed models and how they can deal with non-independent observations, I'm hoping to teach you the basic concepts around the assumption of independence, why it's important, different ways in which it can be violated, and then conceptually what mixed models, a particular type of linear regression model, can do to handle non-independence, and then also how to implement these models in JMP and interpret the outputs that you're seeing. So if you're brand new to mixed models, this should get you from knowing nothing to being functional. And even if you already do some mixed modeling, you're certainly going to maybe reinforce some concepts you already know and learn some JMP techniques that maybe you didn't along the way. Now, before we get started, I want to direct everybody's attention to Zoom's Q&A window. So go ahead and find the Q&A icon in your Zoom interface and open it up. I invite questions throughout. I'll have the Q&A open on my screen as we go along, and should have time at a couple points to pause and see what questions are in there. There's also a Zoom chat window, and if you want to just send general comments to me or my colleagues who are also on the webinar, or to just the attendees in general, please feel free to use the chat. But please do put your questions in the Q&A. It helps us better track those questions and figure out which have already been answered. So with that, then, I see the first question came in. Will this be recorded? Yes, this will be recorded. All of our academic webinars are recorded and posted to the JMP user community and to YouTube. So if you're here, know that you are on our mailing list for this webinar, and you'll receive a link to the recording. And that will also contain the slides and JMP files for today as well. All right, so with that, let's dive in. And normally, if you've attended these webinars before, you know that we get right into JMP and start demonstrating techniques. But for these webinars, we're really focused on upskilling academic researchers. Sometimes we cover statistical concepts more generally. And so I want to begin with just a few slides to lay some conceptual groundwork before we actually start analyzing data. Now, what I'm going to show you largely comes from this book that was published 4 years ago, JMP for Mixed Models, written by my colleagues at JMP, Ruth Hummel, Elizabeth Clausen, and Russ Wolfinger. So the examples we're going to see are all covered in great detail in this book. The book also covers a number of other examples and techniques that we're not going to talk about. It really is a great resource for learning the basics, the foundations of mixed modeling. So you'll get these slides as accompanying the recording, and you see that I've dropped some links in there. So you can find the book in digital or print format. It is not expensive. I think it's on the order of about $40 last I checked. And you can also download the sample data sets as well. I personally learned a lot from reading this book cover to cover. And after today's webinar, even if you don't know anything about mixed models, you'll know enough to be able to really get a lot out of this book, I think. But of course, you don't have to. Just thought I would point you to it in case you're interested. Now then, let's talk about mixed models and handling non-independence in your data. And first, we're just going to start out by reviewing what the assumption of independence in a regression model actually is or means. So I've put in what I'm hoping is very plain, non-technical language at the top what the assumption of independence states, and that is that in a regression, like we have on the left side of the screen there, the residual from any one observation should not be predictable or even partially predictable from the residual of any other data point. So here you can see we just have a basic regression plot on the left. If you remember from even your basic intro stat, the residual for any given observation is just the distance between that observation and the prediction we would make for that observation from our regression, which would be the corresponding point on the regression line. So this observation here has a pretty large positive residual. This observation right here has a smaller negative residual. And we often plot the residuals to check assumptions about, let's say, independence or what we talked about 2 weeks ago, which was the distribution of these residuals and whether it's normal. And we hope to see some random scatter around the line. So here we have the residual value plotted against the predicted value. So that is the point along the line here. And we can see what looks pretty good. I mean, it's just generally random scatter. And this histogram shows us that the distribution is approximately normal. But importantly, the independence assumption says that for any one residual, let's say this one right here, we shouldn't be able to predict it or even partially predict it based on the value of any other residual. So for example, knowing the value of this residual close to it right here shouldn't allow us to actually predict that, oh, well, this residual should probably be up in this high positive area versus, let's say, down here. And in many cases, in regression, this holds, but not always. And there are two forms that we're going to talk about today of mechanisms that violate independence in our data. But before we get there, actually, what I want to do to help us understand why this matters is to formalize this independence assumption a little more. So I'm going to go really light on the notation, the equations today. We're just going to see a couple, but this is one spot. So on the left here, we have our standard regression equation, right? So we have the y, or dependent variable value for the ith observation, or the ith row. So this is just an index. If I equals 1, we just mean row 1 in our data table. That equals some intercept plus the effect of our explanatory variable. So the ith individual has some x value. We multiply it by our regression coefficient. That gives us the regression line itself, and then the scatter around the line of all the individual points is by, for every observation or individual, adding some residual error. So this should look pretty familiar to you. Again, basic intro stat. You may also remember this notation right here, which is just telling us that that residual error follows a normal distribution with a mean of 0 and some variance sigma squared. So that might look like this when, in particular, the residual value equals 3 in this case. And so what we're saying then is, for any observation, go ahead and compute what this total value is, intercept plus x times some slope, and then go ahead and take a random draw out of this distribution that I've plotted here and add that into it or subtract it out to get the final value. Now, the independence assumption then specifically says that each residual is an independent random draw from this distribution. So that is, what you draw for one residual doesn't affect in any way what you're going to draw for any other residual. And this is particularly important because when we make this assumption, that helps us determine what this value is, the variance of this distribution. Or if you take the square root of that, then we're just talking about the standard deviation of the residuals, otherwise known as the root mean squared error, which you may be familiar with. Now, all of this is really important for inference. So this value, again, this variance of this distribution, is used to compute confidence intervals. It's used for hypothesis testing. So if we want to draw inferences about what factors or effects matter in our data, it's really important to get a good estimate of that sigma squared. But if we violate this independence assumption, we can actually get an inaccurate estimate of that, and then it makes all of our inferences not trustworthy. So that's what independence is and why it matters. There are, as I mentioned, a couple primary mechanisms through which we can violate independence. So I'm going to highlight both of them really briefly here, and then we'll dive into each in more detail and see how mixed modeling can actually help address these issues. So the first type of violation we're going to talk about is with respect to grouping or clustering of observations. Specifically, if you take data from different clusters or groups and lump them together, that can lead to the residuals being partially predictable from their group membership. So that's one way in which they would be not independent. So imagine a situation where we have measured students in two classrooms, and we're actually going to analyze the data that I used to make this graph in just a little bit here. So what we've done is we've administered them some kind of pretest score at the beginning of a class, and then at the end of the class, we measure their learning gain. We want to see what the relationship between pretest score and learning gain is, and by this graph, it looks positive. Now, this graph has two different classrooms of individuals, class A in the blue circles, class B in the purple triangles. But if we just lump those together, let's say, we haven't included class as a factor in our analysis at all, we get this general regression line out, So a slightly positive slope here. But you can see just by looking at the position of Class A versus Class B with respect to the line that these residuals aren't independent. Class B is almost exclusively below the line, so negative residual, and Class A is largely above the line, positive residuals. So without accounting for class in our analysis, we have violated this assumption of independence. Now, just to take another look, we often look at assumptions with these residual plots. It's as easily or readily apparent in a residual plot where, again, we're looking at the predicted value against the residual. And we can see here once more that grouping clearly has led to some non-independence. So we'll see how to deal with that in a moment. But first, I want to highlight another primary mechanism for violating independence, and that's in longitudinal data. So data where you take measurements across multiple time points. So in longitudinal data, the residuals can actually be correlated across time. So take, for example, this simple regression where we've regressed United States GDP, gross domestic product, against date, just to get an idea of what the trend is in growth of GDP over time. Now you can see just from this plot that the residuals certainly aren't independent. We have a streak of residuals that are above the line, then it swings below the line, then up and then back down and so forth. And if we were to plot these residuals now not by predicted value, but by time, or that is by row in our data table, if our data are time ordered, you can see this very clear pattern. The scatter around this center line of 0 is not at all random. Now, of course, for this situation, where we're modeling the change in GDP over time, we might use time series models, which can actually handle this correlation across time quite well. But for simple analyses, like a simple regression, this would actually be a pretty serious problem. And it can actually pop up in less obvious ways as well. So consider this example. We are looking at the effect of advertising expense on sales volumes. And we can see that the more we spend on ads, the higher sales we see. Each point here is actually 1 month worth of data. So how much did we spend on ads that month and what were our sales? So even though in our analysis we're not looking at time, time is inherent to the data itself. This is longitudinal data. And if we were to plot the residuals across time, we can, even though it's not apparent in the regression graph, we can see a pretty clear trend. In this case, it's oscillating kind of like this. And so we could see a pretty strong positive correlation at various time lags. So for example, at a time lag of about a year, we keep seeing these peaks or these troughs in the residuals. So another form of correlation across time. All right, so we've established then what the independence assumption is, these two mechanisms for violating it. So longitudinal data, correlation of residuals across time, or lumping together different groups or clusters of data where the residuals are related to that grouping. And now that's where I want to start with the non-independence and grouped observations. We'll talk about this for just a couple more minutes in more detail and then learn all about how mixed models actually can handle this particular issue. So we've already talked about students from different classrooms in this example of pretest score and learning gain. Some other examples could include observing patients at several different hospitals over the course of a medical study. So maybe you have partnered with researchers at several different university hospitals, and each of you are collecting data, sampling individuals. Now, if you lump all those individuals together, you could end up with a non-independence problem, because if there are differences in the types of communities or maybe the socioeconomic status or other things of individuals in that community, maybe slightly different standards of treatment at the hospitals, you could end up with non-independence across groups, where groups are hospitals in this case. I came from cognitive science, where people do cognitive psychology experiments, where you do many, potentially even hundreds or thousands of trials per subject in an experiment. So within each individual subject, that's kind of like inherently a group, and you will have non-independence within those observations within a subject. Consider something like ecology. If you're collecting multiple specimens, let's say plant specimens at different sites, maybe different parks or nature preserves, differences across those sites could lead to non-independence. Or in the example we're going to start with, Sometimes you apply experimental treatments, not to just completely independent individuals, but maybe to pre-existing groups of individuals or observational units. So maybe you get in several different batches of raw materials and you apply treatment one to one batch and treatment two to another batch and treatment three to another batch. Well, differing characteristics of those raw material batches might lead to non-independence in your observations as well. Now, how do we handle it? Well, if you're used to thinking about regression models, let's say we'll go back to the classroom example in the graph right there. We have class A versus B. You'd say, well, let's just put class A and class B into the analysis, right? It'll be a two-level categorical covariate here. And so we'll basically be estimating a different regression for each class. So maybe, but there actually can be issues with that. One, what if in a more realistic scenario you have hundreds or thousands of classes? It might not make a whole lot of sense to actually estimate that many different regressions. Maybe you have varying amounts of data. So for some classes, you only have, let's say, 2 students worth of data, and you want to include it, but you're not going to get a meaningful regression estimate out of just 2 individuals. Or even more generally, maybe you really want to generalize to new classes entirely that you've never observed before. And so it doesn't really matter what the effect for any individual class is. We're interested in the average effect generalized to all possible classes. And so that's really at the heart of the issue. We usually don't care about estimating the effect for any individual group. We want to generalize across all possible groups. And that's something that mixed models can actually do for us. So here's how we're going to handle the non-independence in these grouped observations using a mixed model approach. And here's the approach at a conceptual, like really kind of non-technical level. We're not going to estimate the effect of the grouping variable on the mean of y. So we're not going to include class or hospital or raw material batch or whatever as a traditional effect in a regression model. Instead, what we're going to do is just estimate the variability in y, in our dependent variable, that is due to the group-to-group differences. So let's actually call back to our regression model so I can make this a little more clear. First, actually, I probably should have animated this. Let me go ahead and just kind of scratch a couple bits out here and highlight to you that what we have is just a slight take on the regression equation we already saw. Y equals an intercept plus the effect of x plus some random error. We're just adding in this R sub j thing, where j now is an index for a group. All right, so if we have 10 classrooms, j could take any value 1 to 10. So classroom 1, classroom 2, and so forth. And so what we're saying is that the response or dependent variable for any individual member of a particular group is equal to the intercept plus the effect of our x variable plus a residual drawn for the ith individual in the jth group. But we also now have this term, R sub j. And so by sub j, that means that we have one of these for each group. And then down here, we're saying that this is actually, just like the residual, a random draw. It's a random draw from a normal distribution, mean is 0, with its own variance that we're denoting sigma squared sub r. So you can think about it kind of like a residual, but it's at the group level. We're assuming that every member of an individual group, so an individual classroom or a patient at a particular hospital, gets the same value here. And because it's a random draw, it means any new hospital, we can assume, oh, even if we didn't observe them, well, they're just going to get another random draw of their own. So what we have here are 2 different types of effects in this model based on the factors that we have to put into it. For whatever our x variable is, we have the fixed effect, so the effect on the mean of y of this particular variable, but then we also have an effective group, and that's a random draw. So we call that a random effect. And so with a fixed effect and a random effect in the same model, that's where you get the term mixed effect model. It's a mix of random and fixed effects. Now, you'll notice I said in this example, this is what we call a random intercept model. Well, why is it called that? Well, think about it this way. In a standard regression model, you have some intercept. So that's just the value of y when the value of x equals 0. And for each group, we're just adding a constant value that was drawn randomly. And so if you take these two constants that apply within a group and put them together, they can kind of combine into a single intercept that's group specific. So another way of thinking about it is this R sub j is just an adjustment to the intercept dependent on which group you're in. And so even just this relatively simple mixed model is actually a very powerful way for handling non-independence and grouped observations. And what I want to do now is actually show you a couple examples of how we can do that. So let's head on over to JMP and take a look at the first example. I should mention you're, of course, going to be able to download this JMP journal that you're looking at here when I send around the link to the recording. And you can also find the links from the slides about this JMP for Mixed Models book at the top of the journal as well. So let's actually take a look at an example now of a random intercept model. And this is going to be in the context of an ANOVA. When we looked at that equation, we were talking about just a simple linear regression. But an ANOVA is also just a form of linear model. And so this applies equally well to that situation. Now, in this example, we want to test the breaking pressure of different metal bonds to be able to figure out which one is actually strongest. And here is how the experiment worked. So we have 7 different ingots, and an ingot is just a metal bar. Now, each one's pretty big, and we're resource limited. So what we want to do is cut each one of these ingots into 3 pieces and then apply a different bond type to each piece. So one piece will get a copper bond, one will get an iron bond, one will get a nickel bond. And we do this for each of these 7 ingots, cut it into 3 pieces, and then randomly assign each piece one of our 3 bonds. Here's the data that we have. So you can see we have ingot 1 right here, 2 right here, 3 right here. Each one has the nickel, iron, and copper bond applied, and then here's the breaking pressure when we actually try to break that bar in half again. So in this case, we have a fixed effect of bond type, nickel, iron, and copper, and we also have a random effect of ingot or metal bar here, because we have ingot as this grouping variable inherent to our design. If you're curious about what type of design this is called something called a randomized complete block design. Now, I'm going to pull up some graphs of our data. Just for the sake of time, I'm not going to go into Graph Builder and make them all today. We have plenty of learning resources on Graph Builder if you're interested. But this will give you an idea about how we have non-independence in these data. So on the X, I have bond type. We have 3 levels. We have the breaking pressure on the Y. We have the mean breaking pressure for each bond type, denoted by this line with its confidence interval around it. And each ingot now is just in a different color so that we can easily find it. Now, look, for example, at ingot 3. It's pretty clearly, let's say, a little bit stronger bonds on average than all of the others. That is, it has a pretty high positive residual in all 3 cases. Let's contrast that with ingot number 2, which is in the purple here, here, and here. Quite the opposite. Pretty strong negative residual in all 3 cases. Now, these ingots, I mean, they probably, even though, let's say we got them from all the same place, they have different chemical properties that make them adhere to these bonds more or less. And so we would expect that the overall breaking pressure between them might change a little bit. And so we want to account for that with one of these random intercept models. So here's the model we're about to build. I'll show you how we actually build these models. I just want to give you an idea of where we're going with this. So this is a mixed model with a random intercept. We can see right here, just like we would with a standard regression model, we can get a test of our, in this case, a fixed effect of bond type. And we can see that that's statistically significant, p-value 0.0131. So it looks like, based on our graph, that iron bond type is probably stronger than the other 2. And in a moment, we'll chase that down and confirm that that's the case. But something new that you don't see in a standard regression is all this stuff up here, the random effects covariance parameter estimates. Now, right here, you have the variance estimate for ingot. So if you remember when I pulled up that equation, we had sigma squared for the error, but also sigma squared for the grouping. Here's that estimate right there. It's 11.45 approximately, and it's actually ever so slightly larger than our estimate of the variance of the residual error. In fact, if you break down all of the variance that's not explained by our bond type, 52% of that is actually attributable to ingot differences, and about 47% is attributable to residual error. Now, there's more to navigate in this report than that, but that's the basic finding. Bond type matters, and it looks like the variance associated with ingot is, relatively high. It's about the same amount that we would attribute to residuals. But now let's back up. I want to show you how we actually fit this model in JMP. So I'm going to go to Analyze, Fit Model. Fit Model, if you're not familiar with it, is just a general purpose linear modeling tool with many different linear modeling approaches or techniques in it. For example, standard least squares, or what we're going to be doing today, mixed model. So while I choose mixed model here, I want to point out I'm using JMP Student Edition 18.2. JMP Student Edition and the more advanced version of JMP software, JMP Pro, they both have mixed models. And I stated that imprecisely. JMP Student Edition has all of the capabilities of JMP Pro and is free to use for any academic, so in a research context or in the classroom. If you are not coming from academia, we always have a few non-academic folks at our academic webinars. If you have just standard JMP, you actually aren't going to see this mixed model personality here. So if this is something particularly useful to you, that's a good reason to maybe check out JMP Pro. All right, with that said, now let's actually specify our model. You'll notice we have a role for our y variable, that's braking pressure. And down below where we construct our model effects, notice these two tabs right here, fixed effects and random effects. Well, we said our fixed effect is just bond type. So a 3-level categorical factor equivalent to just a one-way ANOVA. And our random effect in this case is ingot. And by putting just ingot in here, what I'm saying is that I want a random intercept for each level of the ingot. But again, treating them as a random draw, not modeling each one independently. So I'll click Run. And now we're back to the output that we started with. So let me just minimize some things. So again, here's our effect of bond type right here, statistically significant. Here are our estimates of the variance associated with ingots and with the residual error. Now let's explore these results a little bit more to give you an idea of how to navigate this report and interpret what you're seeing. So first off, once you've assessed the fixed effects and the random effects, you might want to, having determined that your model seems appropriate, investigate the fixed effects a little bit further. So there are a number of different ways to do that. If you're a JMP user, you probably know about the prediction profiler, a great way to visualize your model and the predictions that it makes. Now, when you go to the red triangle menu here in the mixed model personality, you're actually not going to see something that just says profiler. Instead, you're going to find these two sections, marginal model inference and conditional model inference, and you'll notice that profilers live under each one. Generally speaking, if you're just interested in the average effect for your X variables, your fixed effects, go to this marginal model inference and choose the profiler. And I'll talk about how this is distinguished from the conditional model inference in just a moment. So here we can actually see the predicted means for each group. So here, the predicted mean breaking strength for the copper bond type, 70.2 approximately. Iron much higher at 75.9. Nickel back down at 71.1. Now we can actually get these out of the fixed effects parameter estimates as well. So if you're looking at parameter estimate tables, here are where you can find the fixed effects parameter estimates. So for example, with indicator coding here, where our baseline level is the nickel, you can see that the intercept is estimated at 71.1. That corresponds to the 71.1 down here. Copper is actually almost a full point breaking strength lower than that, which we already saw right here, down to about 70.2. And then we're actually 4.8 points higher than nickel when we get to the iron bond, which we saw here, 75.9 versus 71.1. All right, so we have our fixed effects parameter estimates Finally, we might want to actually do some pairwise comparisons. So is it the case that iron really is stronger than nickel, really is stronger than copper? Is this difference between nickel and copper statistically significant? I probably doubt it, but we always want to check. So under the red triangle now, I'm going to go to multiple comparisons, which allows me to do these follow-up tests, in this case on bond type. I'm going to ask Jump to show me a plot of the means. It's actually going to look, in this case, just like this profiler plot, and give me all the pairwise t-tests between these different bond types. And so we have it below. Here are those same means we saw in the profiler. Here is the graph of those means. And then down here we have the t-tests. And we can see that if when you compare copper versus iron, that's a statistically significant difference. Copper versus nickel, the second one down, is not statistically significant. Its p-value is all the way up at 0.6. And then iron versus nickel, that's a significant difference as well. P-value of 0.016 approximately. So what can we conclude? Well, iron is stronger than both nickel and copper, and nickel and copper are not statistically different from one another. So now what I want to do briefly is contrast this with what would happen if you actually didn't build one of these mixed models. So let's say that I just ignore ingot and look only at bond type in a traditional one-way ANOVA, which you could do if you're familiar with fit y by x, but just to keep things consistent, I'm going to stay in fit model today. So here I'm just going to say model breaking pressure as a function of bond type. Let's just pretend ingot's not there and click run, and we'll see what happens. Well, let me simplify our outputs a little bit here so that we can concentrate on what's important, and that's these effect tests right here. You'll notice that if we don't account for the variability associated with ingot, which we've not done on the left, we no longer have a statistically significant effect of bond type. So the inference that we would make from these data fundamentally changes based on whether or not we account for the non-independence in our data. And you might be saying, okay, well, what? Like, why? Why does that happen? Well, look at it this way. I'm going to go back to our random effects covariance parameter estimates here and highlight that the ingot to ingot variability is about the same size, estimated to be the same size as the residual variability. If you ignore the ingot to ingot variability, a lot of that's probably going to get absorbed as or represented as residual variability. And you can actually see that when we get over here to the error. 21.8194, which notice actually that's kind of the total of the ingot and residual variability right here. So by assigning some of the variability to ingot, we've actually essentially increased our statistical power to be able to detect the true effect that happens to be there. So if you have non-independence among groups, it can actually maybe be to your benefit in some cases to represent that appropriately here. Now, I want to point out a couple more things with respect to these random effect covariance parameter estimates before we move along. One is that you actually get a p-value associated with them. I've kind of been avoiding talking about that right now. Now I'm going to tell you why. You can see here that the p-value associated with that ingot-to-ingot variability is not below that typical 0.05 threshold, 0.19 approximately. And so you might conclude, oh, well, there is no ingot-to-ingot variability. I don't have statistical evidence of that, so maybe I should exclude it. As we saw, if you exclude that, then you actually no longer have a statistically significant effect of bond type. Maybe now we're starting to get into some kind of p-hacking scenario. It's important to remember that what we're really trying to do when we build these models is have a model that accurately reflects reality. So we don't want to just blindly follow p-values as our guide, really ever, but certainly not in this case. We might know a priori, like these ingots that we get, they aren't chemically identical every time. There absolutely will be some that adhere to different bonding agents more or less strongly than others. So even though I know, or I see, excuse me, that I don't have a statistically significant effect here, I know a priori this variability is real. There is ingot-to-ingot variability and it belongs in my model. And so that's why I would choose to leave it in there, regardless of what I saw here. Though if I saw a really high p-value and a really low estimate right here, I might start to ask questions and question what I believe to be my, my pre-existing knowledge. We just don't have that situation right here. Now, one other thing to say about the random effects is that while we haven't estimated in the model terms or parameters themselves what each ingot's actual value is with their random intercept, you can obtain those after the fact. That's what you're going to find under the random coefficients. So if you remember those R sub j terms, here they are. So ingot 1's adjustment to the intercept, negative 1.55, negative 3.7 for ingot 2, positive 4.07 for ingot 3. And this makes sense. If you remember, ingot 2 was consistently negative residual, so we're adjusting its intercept down. Ingot 3, consistently higher, so we're adjusting its intercept up. These just aren't terms in the model. We're just taking the model that we've built and then figuring out, well, what's the highest probability value of that R sub j for each ingot given the model? It's a subtle but important distinction. You'll sometimes hear these referred to as BLUPs, best linear unbiased predictors. In fact, you can get a fuller table on information for these BLUPs or these random coefficients. Under the model reports, you can go to random effects predictions. And now here you're actually going to see in the full table, we give them the more, statistically accurate name BLUP, and you get your standard errors and confidence intervals on them. So if you are interested in looking at, how specific levels of your blocking factor, your random factor differ, you can do that by looking at these. I'm not really going to focus on it today. I just wanted to point that out. All right, so that was a lot, but that's kind of the big fleshed out example that hopefully can help establish a lot of these really important concepts with respect to mixed modeling using ultimately a pretty simple or basic scenario where we just have a one-way ANOVA with random blocks or random intercepts here. So I'm going to take a moment, take a sip of some water, and check out the Q&A. See what we have here, if there are some good ones to answer now. Okay, so somebody asked, what if you don't know the grouping a priori? So you sample sites along a line, and half the line is ecologically different from the other half. Okay, so let's see. Right, so maybe you don't know that there's some naturally existing grouping. That's something that you could investigate. So if you have some reason, any reason to believe that there could be variability across groups, you would have to find some way of declaring what those groups would be and then create a model where you actually try to estimate that variability. So that's, ultimately more exploratory kind of analysis where you might have to rely more on, p-values and confidence intervals. But in general, if you have a priori reason to believe that some variability is going to be introduced across, different groups, even if you don't know what those groups are, you probably want to try to account for that in some way, or at least, explore the possibility. Let's see, what about if there's an interaction between fixed and random effects? Interesting. So you can declare interaction terms, if I'm interpreting this correctly, between what you would use as a fixed effect and then also a random effect in the model. What that essentially does is create a new random effect at the intersection of levels of a fixed effect and levels of a random effect. That can actually lead to confounding in the analysis between residuals and random effects. It kind of starts to get messy. So all I'm going to say there is, if I'm understanding the question correctly, what you're saying is possible, though not always able to be estimated or even necessary. All right, let's see. Oh, there's some even more questions. So I'm going to get to as many of these as I can, but probably won't be able to get to all of them live. I want to stress right now that when you get the follow-up email with the recording and everything, you are free to ask questions in there as well, and we can answer them. Let's see. Oh, I just got one. How does it work with longitudinal data? Well, that's where we're going to head in just a couple minutes, so that's great. What is the minimum group size? Well, let's see. So the minimum group size in this case. I mean, it kind of depends on what your specific goal is. I think as low as 1 if the design is correct or what you're trying to estimate is supported by that, though that's obviously, generally speaking, somewhat problematic. But that's also the benefit of this approach over, say, standard least squares models, like, or if you were going to do, let's say, a repeated measures ANOVA on data, like the example that we're seeing right now, is that you can actually have varying group sizes or missing data and still be able to use all of the observations that you have. Let's see. Okay, I'm going to try to get to maybe one more right now. Thank you all for sticking with me here as I try to get it to as many as we can. Um, Here's one. What is the um, denominator in degrees of freedom denominator under random effects predictions? Okay, let's see. So the random effects predictions, this degree of freedom denominator. Oh, okay. I've misunderstood the question. I thought you were looking first for the fixed effects, which would just be in a typical F test here. I'm going to have to get back to you on how that degrees of freedom is actually approximated here. One of the challenges with mixed models is actually you don't have the direct calculation of degrees of freedom, much like you do in standard least squares. Um, so degrees of freedom, for those who aren't familiar, it's essentially an estimate of how much independent information there is in your data. And when we're trying to estimate models with non-independence among observations, it becomes more challenging and you have to use degree of freedom approximations to actually create those estimates. So this is coming from one of those, but off the top of my head, I do not recall the specifics. I will say that you can always click on the help tool in JMP, this little question mark, and highlight certain parts of your report and click in to get more details. And so that's where I would go here. It looks like my browser is kind of hanging a little bit. So actually here we just got the random effects predictions. I'd probably go down to the statistical details in this case and try to find some more information there. For the sake of time, we won't do that right now. We're actually going to move on, though. I'm glad to see so many questions coming in, far more than I anticipated, actually. This is definitely a hot topic for folks. So I'm going to encourage you again to please, if I don't get to your questions or in full detail even today, to ask those questions when we follow up with you, and we'll be happy to help out. Now, I do want to briefly highlight a second random effect or mixed model situation that's pretty common. And it's going back to the classroom example that we talked about before, where you're assessing the relationship between somebody's pretest score at the beginning of a math class and their learning gain exhibited after the course is over, where learning gain is just you take a post-test and then you subtract out the pretest and see how much better they did on the post-test than the pretest. And so in this particular situation, we've randomly sampled 190 classrooms, and each student was given within the randomly sampled classroom. So here, class 1, 2, and 3 were sampled. There are some classrooms out there in existence that we did not sample. Each student was given the pretest at the beginning of the course and the post-test. We have the data right here. So 190 classes, 3,691 individual students. We have each one's pretest score and their learning gain. And you'll notice that the classes are of varying sizes right here. So we have 38 students in class 109 versus I think we get as low as maybe 12 students in some of the smaller classes. Now, as we talked about in the outset, class is obviously a grouping factor that could lead to non-independence here. If I make a quick graph of the data, you can see for just the first 5 classes what the regression models look like for those 5 classes. And so you can see the intercept would be different for each class. So just trace each regression line back in this direction, and you can see how the intercepts would be, in some cases, wildly different class by class. And so the intercept in this case is just the learning gain for somebody who knew nothing and got a 0 on the pretest. You'll also notice that the slopes of the lines look a little bit different as well. So it's not the case that just the intercept seems to, vary by class, but the slope does too. So oftentimes in these kinds of cases, what you want to do is have 2 random effects in a model where you have intercepts and random slopes. So the model will estimate the average slope of the regression line across all classes. and then assume that for any individual class, you have some random adjustment. Maybe make that slope a little more or less steep depending on the class. So just to drive this point home, if we fit a model equivalent to the one we did for the metal bond example, we would just have random intercepts. We would assume that underlyingly every class has the exact same relationship between pretest and gain. Now that's probably not true. I mean, different instructors maybe have different techniques, different levels of efficacy, and we might see a different relationship and instead believe that something like a model that respects the random nature of the intercept and the slope is actually more appropriate. And so that's what we're going to fit right now. Let me show you how to do that. So I'm going to go back to fit model. We're going to put gain in as our y, pretest here as our fixed effect. Let me change to mixed model. And now under the random effects, if we wanted to just do a random intercept model, we would just add class to it and be done with it. But if what we want instead is a random slope model, what we're going to do is take the variable for which we want random slopes, that's pretest, and then select that while also selecting the grouping variable, in this case class, and I'm going to use this button, nest random coefficients. And what this is saying is that each class should get a random intercept, and each class should get a random slope for the pretest line. So I'll click OK. Let's simplify our output a little bit here and just briefly walk through. Do we have a statistically significant effect of pretest? We do. Vanishingly small p-value. What's the variability associated with the intercepts? That is the learning gain for somebody who gets a 0 on the pretest. Well, it's 14.5 approximately. So it's coming up on, about, or a little over, half of the residual. Here's the variability of the pretest slope. So a fair bit smaller than for the intercept, but nearly statistically significant. You're also going to see, and I'll cover it in just a second, that we actually modeled the covariance. You could think of it as the correlation between these two distributions, so the random intercepts and the random slopes. But first, if we want to follow up on that fixed effect result that we saw, we could just look at the parameter estimates, and here's the slope for the regression line, negative 0.186. So basically, the more somebody knew at the beginning of the course, the less they're going to learn overall, probably because they had a higher baseline. We could, of course, pull up the profiler for the marginal model inference, where I can't remember if I said this explicitly before, but marginal model inference just means marginal across all the levels of our grouping variable, so all classes. So here is the average regression line and the predictions that we would make for the average class given their pretest score. Now, briefly then, let's look at marginal model inference, or conditional model inference. And this just means conditional on which class we're talking about. So let me expand that a little. And so here I have class selected as 1. So if we use the BLUPs for class 1, here's what the line would look like, given its best estimate of its intercept and slope. And you can see the intercept and the slope changes class by class. So we've pulled out these BLUPs. So again, that is the random coefficients or the random adjustments to the intercept and slope for each class right here. And we're being able to visualize then what the final model would look like with those adjustments using this conditional model profiler. And the language conditional also applies when we're looking at our actual by predicted plots, where this first one is marginal across all classes, and this one is actually taking class into account. Now, finally, I mentioned that we actually see a covariance here between our random intercept and slope. And you can actually see that here if I go to make into data table for our BLUPs and just do a quick graph, that in fact, these are correlated with one another. The correlation being negative 0.73. So the larger the intercept, or the more positive the intercept, the more strongly negative the slope in this case. And this is common in these random slopes or random coefficient models, that you include this correlation between the two. That is, that the random draw of an intercept is not independent from the random draw of the slope. So this is just another really common type of mixed model that you're going to see. And again, how to fit it in JMP. Uh, we are already running a little bit short on time, so I want to make sure we give enough time to talking about autocorrelation in repeated measures data. So let's jump on over to talk about that briefly here. We may have to skim over a couple of the details, but let's set the stage here. So if you recall, oops, here we go. We mentioned that if you have longitudinal data, so data that's measured across time, you can have correlation among residuals. And we saw that when we have monthly data on ad spend and sales, you can actually see the correlation across time of the residuals here. In this case, we have this oscillating pattern. I've put some more examples of situations where you can have this, but really any longitudinal data can exhibit this kind of pattern. And the pattern can also expand across space as well. So for example, if you take soil pollution levels at increasing distances from the center of a waste disposal site, you would expect a correlation between two observations at particular distances from the center. Now, crucially then, any correlation in these repeated measures or longitudinal or spatial data has to be accounted for in some way by the model in order to, again, get that accurate estimate of residual error to be able to form accurate inferences. So here's the idea of how we're going to use mixed modeling to do that. We're going to assume a particular way in which observations are correlated across time points or maybe across spatial distances. And then we're going to estimate covariance parameters, kind of like we were estimating variance parameters before, but these covariance parameters actually tell us how much correlation among all those observations we should have, or how much variability in our data is due to those correlations, giving us a better estimate of what the residual error actually is. So let me just unpack that with one specific example. Here's one model that will fit right now. It's a regression model, often called AR1. It stands for first order autoregressive structure. The basic idea is that for any two adjacent time points, so if this is you're measuring things weekly in a medical study, it'd be week 1 versus week 2, you assume that the correlation is the same. And we'll denote that with some parameter R. So between time 1 and time 2, the correlation of those observations is R. Between time 2 and time 3, well, that's also R. Time 3 and time 4, that's also R. Then when you get into greater gaps, you just start taking that to higher powers. So if you have a gap of size 2, so time 1 to time 3, well, that'll be R squared. And time 2 to time 4, that would be R squared. Once we get out to a time lag of 3, well, then that would be R cubed. What this amounts to is the correlation falling off exponentially at increasing time lags here. So let's say that we estimate this R parameter from our data to be 0.9. Well, here's what that actually says. The correlation between observations that are just one time point apart are 0.9. Then at two time points apart, or a lag of 2, it's 0.9 squared, so that's 0.81. A time lag of 3, well, that's 0.9 cubed, that's 0.73. And you can see that the correlation just falls off exponentially. Now, this is one type of way in which the observations are correlated, or one assumption we would make. This might not actually represent reality. You could have some other ones. I'm not going to walk through this. You'll get the slides. You can see that. But another common one just says, okay, well, we're just not going to assume R squared, R cubed. We're going to estimate a separate correlation at time lag 2 and an even separate one at 3. And that structure might look quite a bit different, or how that falls off. There are many different possible correlation structures you could use. But let's just see how we fit one of these models in JMP before we run out of time here. So in this particular example, we're going to test 3 drugs' effect on asthma patients' respiratory ability as measured by something known as, I think, the forced expiratory volume at 1 second. So that is just how much air can somebody breathe out in 1 second, where you want to see a higher value for somebody. If you have asthma, it might be hard to actually breathe. So you first measure a baseline FEV value for your collection of subjects. Then you randomly assign those subjects. They either get a standard drug A, an experimental drug C, or a placebo. Then you wait an hour and you measure their FEV1 again. Hopefully it's gotten better from baseline, at least for the two drugs. And then you just keep doing this hourly to see what the effect over time is of these three different treatments. So I'm going to pull up the respiratory ability data here. You can see we have our each individual patient. So here's patient 201 who received drug A. Here's their baseline FEV value. And then here's the hour at which they were measured and what their FEV value was as well. So what I want to do is fit a mixed model that respects the correlation across time of these FEV1 values here. So I'm going to go to fit model, to our mixed model personality, say FEV1 is what I'm interested in. I want to control for their baseline FEV1, so I'm going to include that as a covariate. And then I want the effect of the drug they took, the hour at which they were measured, and also the interaction to see if the trajectory over time for these different drugs differs. So here we have that interaction term. Now, we had been spending time in the random effects. I'm going to actually go over to repeated structure now because that's what we're dealing with. We have this repeated structure, in this case across time, that we want to account for. And here are all of these different covariance structures that we might use. You can see this AR1. The other one I mentioned very briefly is something called a Toeplitz structure, and there are many more as well. Here are 4 spatial structures down here. I've included a link right here in the journal where you can learn about all of these different structures, but the idea is to often try multiple and see which one fits best if you don't have an a priori reason for choosing one over the other. So I'm going to choose that AR1 structure that has that exponentially decreasing correlation. I'm going to say that patient is my subject, so we're going to be estimating the correlation using the data within each subject. And then we're repeating our measurements across time. And I'm going to use this numeric version of our hour variable because when you're doing an AR1 model, this variable that presents the time needs to be in numeric format. So I'll click run, and now we have the final model out. And because we've walked through a number of these examples already, I'm not going to spend a ton of time interpreting these. But you can see, for example, we have a statistically significant drug by hour interaction. So if we were to pull up the profiler, we'll go to marginal model inference and get that profiler, we can see the effective baseline on average across all the subjects. Here we have the effect of drugs. So we can see, at least at the first hour, slightly better respiratory performance in drug C than drug A. Certainly lower for the placebo because it wasn't a real drug. We can also see the differences at the various time points. Now, I could even do multiple comparisons just to give you a quick example. We're going to take a look actually at maybe, let's compare every time point to a control. What I'm going to say is for every drug and every time point, compare it to the first hour, the placebo is kind of a baseline. And we can get a plot out. So the placebo is in red here. We can see that both drugs first have an effect and then over time start to fall off. And if we look at the results of statistical comparisons, we can see that for drug A, looks like the first 2 hours are better than the baseline. And then after that, it's statistically indistinguishable. Our new drug, drug C, you see 4 hours of benefit over baseline before falling back down. And so we might be able to say that, drug C has a longer lasting effect than drug A here. Now, if we go back up to our repeated effects estimates right here, if you remember in that AR1 model, we said we're just going to estimate that one covariance parameter and then assume that it just falls off exponentially. And so here is that estimate compared to the residual. Now, of course, we could try multiple different models. Let me just relaunch the analysis and say instead of an AR1, I'm going to do that Toeplitz model that I mentioned briefly. And so that's one that's going to allow me to not assume exponentially decreasing. It's just going to estimate a different covariance at each time lag. And I click run, and now you can see I have all of those different estimates right here, one for each time lag, of which we have up to 7 in our data. The basic inferences stay the same here. I have a statistically significant drug by hour interaction. What I might do here, if I didn't know which to choose, there are a number of different techniques, but a simple one is to take a look at the fit statistics. So let me highlight both of these right here. And in particular, look at these AIC and BIC values. These are going to tell us basically how well-fitting the model is with a penalty for how more complex it is. So we have more estimates here in the Toeplitz model. So it's more complex than just the single covariance parameter estimate here. What we're looking for is lower values of an AIC or BIC over here to tell us that it's worthwhile actually estimating those parameters. And if you look, 201 and 341 are lower than 237 and 352. So actually, in this case, I might prefer this Toeplitz model. For the sake of time, I'm not going to reproduce this final analysis, but if you did in this case, and you can because you'll get the data for these, you'll find that the inferences we make luckily don't change. So that's a little bit on handling longitudinal data. We didn't have an example with spatial data, but the ideas are pretty similar. It's just we're talking about extent over time as opposed to over space, and there are certain correlation structures you can impose for those as well. And we've hit the top of the hour, so I apologize tremendously for not getting to the final example, though you can check it out on your own. It is for generalized linear mixed models. So if you remember 2 weeks ago, we talked about generalized linear models. So that is linear models that assume some distribution other than the normal distribution for the response. You can do that in a mixed model framework as well. And I have an example built in here that would allow you to explore that in a little more detail. And I'm happy to answer any questions you might have about that, either right now or if you ask them in response to our follow-up email to you.